In this module, we're going to be looking at the idea of dissolution, where one compound dissolves into another compound. And when that happens, we call the compound that's dissolving the solute, and the compound that's dissolving into the solvent. Usually the solvent is a liquid. Oftentimes it'll be a gas. Now and then, rarely, it will be a solid. And so the reason we care about this is when compounds react, which is what chemists really care about, when compounds react, they need to get at each other on the molecular scale. And what happens is if you have a solid, this is a solid nickel 2 nitrate, hexahydrate. It's really pretty solid. And if this is going to react, it turns out that it's crystalline solid, and almost none of the nickel 2 ions that are in here are on the surface of the crystals, which is the only thing, if it's reacting as a solid, that could interact with some other chemical compound. To look at how atoms on the outside of a surface are accessible and those on the inside are not, we're going to use a two-dimensional example using squares. And so in this first example, we have a 2 by 2 square, so we have 4 atoms, and all of those are available for attack by other atoms on the outside. So we have 4 divided by 4, and 100% of those atoms are available. If we have a 3 by 3 box, we have 9 squares obviously total, but 1 is not accessible because it's on the inside. And so 8 out of 9 are available. And so that is 89%. If we have a 5 by 5 box, there's 25 overall. There's 5, 10, 13, 16 are on the perimeter. So 16 25ths, so that comes out to 64% are available. And if we have a 10 by 10 box, what we have is we have 100 atoms total, and the amount that are on the perimeter and are therefore available is 20, 28, 36, so 36%. So in a 10 by 10 box, only 36% of the atoms are on the outside, and 64% are on the inside and unavailable. So to look at this with larger structures, I made an Excel sheet that shows larger size squares. And so if a square, it's 400 atoms on a side, only 1% of the atoms are on the perimeter and available. 99 out of 100 atoms are not available. If you have something that's 2,000 atoms on a side, 0.2% of the atoms are available. So 2 out of 1,000 are available. And so you can think about it, if you have an actual crystal, that's 10 to the 20th atoms on a side. And so very, very, very few, a vanishingly small fraction of atoms on the surface are available to react. And so what we do is, because almost all of those ions are on the inside, and very few on the surface, what we do is we dissolve it. And when you dissolve it, you make this. It's a solution of that same compound dissolved in water. When you dissolve it, all of those nickel 2 ions separate from the solid lattice and are now all available to react. And so we've taken a sample for which almost none of the ions are available to react, and now all of them are. And so what we're going to be doing is we're going to be looking at a series of different kinds of chemical systems and how they dissolve. And we're going to start with metals and how we can dissolve metals. And you don't usually think of metals dissolving, and they don't usually dissolve. So what we're going to be doing is we're going to be looking at ways of getting metals to dissolve. And after that, we're going to be looking at ionic compounds. And many ionic compounds, like salt, dissolve readily, and we'll talk about that a little bit. But mostly what we'll be doing is we're talking about how do you get ionic compounds that are normally not soluble to become soluble? How do you force them to dissolve? And finally, we'll be looking at the solubility, or what's called miscibility, of molecular compounds together. Molecular compounds are kinds of normal neutral molecules that you think about, like water and carbon dioxide and alcohol and sugar. And in many cases, those kinds of compounds will mix together well and dissolve together, be miscible, and many times, like oil and water, they do not. And so we're going to be looking at examples of that and analyzing ways of predicting whether they can dissolve, whether they're likely to dissolve, and we will also look at ways of getting them to dissolve together if they're not inclined to do so.